Good morning, Earth scientists. Ready for set 3 of your notes, or section 3 of your notes. Today we're going to start talking about how we classify different stars and the different, we'll eventually get to the different parts of their life cycle on another day. But, so all stars do not look alike. Not every sun or every star looks like our sun, pictured here. These are some other stars and planets as well, so you can also get an idea of size. There are 4 things we look at when we classify stars. We're going to look at what's called an apparent magnitude, an absolute magnitude. You'll also see that as luminosity, and then color and temperature, which are definitely related. So apparent magnitude is the brightness as we see it from Earth. So an early Greek observer named Hipparchus could only see separate stars separate stars into about 6 categories. We call those magnitudes. So you can think of those 2 words as the same thing right now. Magnitudes go in order from 1 being the brightest and 6 being the dimmest. And then he just kind of ranked them in between there. After the invention of the telescope, the scale expanded to include stars that he couldn't see with his naked eye. And then each magnitude is approximately 2.5 times brighter or dimmer than the star next to it. So if we have a magnitude of 2 and a magnitude of 3, one is 2.5 times brighter than the other one. All right, the Hubble telescope, which we talked about Hubble the other day, can identify a magnitude up to 30, which is approximately 1 billion times dimmer than what we could see in the sky without a telescope. So apparent magnitude is apparently what we see from Earth as far as brightness goes. When we talk about absolute magnitude or luminosity, it's the actual true brightness of the stars, not counting for the distance from Earth. So it's like if we set it away at a standard distance, like a light bulb 10 feet in front of me, how bright would it be? Even if that light bulb is in a house down the road, but it's got a brightness to it. All right. You can also think of a light bulb in your living room. As you back away further and further, it gets darker or dimmer, but the actual light bulb itself isn't changing. It's just our viewpoint of it. So that's why absolute magnitude is a little bit more important. It measures exactly what that brightness is, and then it helps account for the actual brightness of it versus how we see it from our Earth sky. Here's just some example suns or stars in our universe and how far away they are from us. And it kind of shows you their apparent magnitude versus their absolute magnitude. And we'll talk about the scales maybe a little bit later. But you can see that just because it is very bright, it can also be very close. So that's why we had to go into the negatives as well. And when we talk about temperature and color are directly related. So it's a correlation between the 2. Based on the color, we can tell the surface temperature of that star, give or take, obviously. Very hot stars with the surface temperatures above 30,000 Kelvin emit the most of their energy in a short wavelength light. So if you know your rainbow, you know that the blue-violet end of the spectrum is short wavelength. That's why they appear bluish in color. It's higher energy and giving off that blue or violet color. Red stars are typically a lot cooler, less than 3,000 Kelvin, still really hot, but still cooler among the stars, and emitting most of their energy is longer wavelength light. So at the opposite end of the rainbow, we have the red, which is longer wavelengths. stars around 5,000 to 6,000 Kelvin, kind of like our sun, appear more yellow. So it's kind of, this is the stellar rainbow of stars, I guess you could call it. Now, there's a pattern that we found with size and color and luminosity of stars, and it's put in what's called the Hertzsprung-Russell diagram, or abbreviated the HR diagram. It's a graph against luminosity and the surface temperature color. So we have our luminosity magnitudes right here. This is 1. Luminosity, we tend to give our sun, because it's the most important to us, a value of 1, and then it gets brighter and dimmer. All right. Then you also have your temperatures. So you have your red colored stars over here, your blue-violet colored stars over here. Knowing the star's classification also helps us know where it is in its evolutionary path. So they have a birth, life, death cycle just like anything else. So we also know it moves through these different categories. Our sun is part of the main sequence, which we'll talk about later. But we also have supergiants, giants, and white dwarfs. We also have black dwarfs too, which aren't listed on here because they're not really functioning stars anymore. All right, so our main sequence, approximately 90% of all of the stars that we know of in the universe are main sequence stars. So they fall along this middle range right in here. They are very stable at this point, like ours is only halfway through its life cycle, just barely, and produce energy by fusing hydrogen into helium in their cores, and that's what makes them burn. The absolute magnitude is directly related to their mass, and that's why it runs diagonal across the diagram. So you have your small and hot, and then your dim and cool. All right, so giants and red giants are right in this category right here. You'll see it labeled as either one, because as you can see, there's no bluish color involved in the giants. So that's why they often get called red giants. They're very luminous stars that have had a larger diameter, but they're generally pretty cool. There's supergiants at the top. They are even bigger than giants, and this is kind of the end of the life cycle. So when they reach this point, when our sun reaches this point, it'll actually reach the giant point. It's getting there. It's just about done. It's about to burn out. And then we have our white dwarfs down here in the bottom corner. They are faint in luminosity, extremely small compared to the main sequence, and again, we'll get into the specifics later on, and generally very hot. So that's why they're in the more blue or white spectrum, which is why they get called white dwarfs, because they're white and hot, and they are very tiny. All right, the last thing you've got to do is watch this video. It does, because it's a textbook-related video, you will have to use your browser for it, so that's why the link is also there. It explains some of the spectrum as well as going into the HR diagram classifications. There's a few questions in your note packet for it. Have a good day.